We are going to continue using the sandwich theorem. Today, we're going to use it to prove this limit, that the limit is x approaches 0 of sine x over x is equal to 1. And you remember when we looked at this one the other day, right? We actually graphed this one and looked at it. There it is, sine x over x. And we looked at it and we said, oh, sure, looks like it's 1, even though we know that if we try to go to x equals 0, it'll tell us that the function's undefined there. Sure looks like it's hitting 1. We even zoomed in and said, doesn't look like anything weird's happening. Looks like it should be 1. But we want to be sure that it's 1. And so in order to be sure that it's 1, we're going to go through this wonderfully long and complicated process. It's not really that long or complicated, but I'm going to say that it is anyway because that's what I do. Using a unit circle. So we're going to say that this thing that I've drawn on here is at least half of a unit circle. And in that unit circle, I have drawn a lovely little radius here and another lovely little radius here. And I've connected those two radii with a line to make a triangle. I'm going to now outline that wonderful triangle here in red. That's the first thing that we're going to deal with. Now, before we deal with that, let's label our picture a little bit. So first off, there is an angle here. Everybody agree that there's an angle there of that triangle?
Yep.
Yeah, you all made it through kindergarten. That's good. There is an angle of the triangle. What should we call that angle?
Theta.
Theta sounds like a good choice, but I've already got a sign of x in here. So can we make it x? Are you okay with that?
I am okay with that, yes.
All right, spectacular. If I'd written like the limit is theta approaches 0 of sine theta over theta, then we'd put theta there and it would all be exactly the same except with thetas. So let's call that x. What else? If this is a unit circle, what else can I label right off the bat?
The radius.
Yeah, and I have two of those, right? I have two different radii drawn. So this ought to be 1, and this ought to be 1, right? They're both a radius of that circle. They should both be 1. Anything else based on this being a unit circle with an angle x here that I should know?
You could label the height, or height of that triangle as sine of x.
Excellent. And I could do that because the x coordinate on the unit circle of a point is always cosine and the y coordinate is always sine. So I could, if I wanted to, label this little piece here as cosine x, although we're not actually really going to need that. So we got cosine x and sine x, and this point here is the point cosine x comma sine x. Everybody good with that or no?
Yep, all good.
Wonderful. All right. Now, let us find the area of that triangle. What is the area of the triangle that I've outlined in red?
Sine x over 2.
And how did you get that? Just 1/2 base times height, right? 1/2.
Yeah.
The base is 1 and the height is sine x. So I got something right out there. There we go. 1/2 sine of x. Everybody agree that that is the area of the red triangle?
Yes.
Yep.
Okay. Next up is not a triangle. Next up is the sector of the circle, a little pizza wedge cut out of that. I want to find the area of that. How do we find the area of the sector of a circle?
X out of 360 times the area of the circle.
Perfect, except that we're going to do it in radians, not in degrees. So
Okay.
x radians out of 2 pi radians times the area of the entire circle, which would be pi times the radius squared. Everybody agree with that? Hopefully.
Yes.
And what does that come out to be? Just x over 2, right? The pi and the pi will cancel. This one's in the numerator. That doesn't look like it from how I drew it, but pi's cancel. The 1 squared is just 1. It's just x over 2. Everybody good with that or no?
Yes.
All right. And the last thing I'm going to ask you to find using this picture is the area of this last triangle. And I should have done this at the beginning. I should have told you all that should have told you all that these are right angles and these are right angles, but I forgot to tell you that. What's the area of that triangle? Well, it's 1/2 the base, which is 1 times the height. What's the height?
1.
Yeah, that's everybody's favorite answer today. The height is not 1. It would only be 1 if that was a 45-degree angle. Sorry, what did you say?
10.
I still couldn't hear you. I don't know, I'm breaking up or something on my end.
Tangent.
Tangent. Yeah. Yeah, that's tangent x. And a couple different ways we hopefully could see that that's tangent x. One way is just that we know that the tangent of this angle x ought to be the opposite side over the adjacent side if this is a right triangle, and it is. So tangent x ought to equal height over 1, which gives us tangent x, which should give us an area of 1/2 1 times tangent x. Everybody good with all 3 of those areas that we found?
Yeah.
All right. Well then, next up is relating the 3 together using an inequality, because we're trying to use the sandwich theorem. I've now got 3 different functions. Let's relate them using the inequality that we normally use for the sandwich theorem. What can you tell me about the triangle that is inside the sector of the circle in comparison to the sector of the circle in terms of area? The thing inside had better be
Smaller.
less than? Yeah, it better be smaller than. We could also just say less than or equal to, because we could, right? If it's less than, it's definitely less than or equal. And what about the sector of the circle? Well, it better be less than or equal to the thing that extends out past it, but includes all of it. True? Everybody feel good about that?
Yep.
Perfect. All right. Now, all we have to do is, instead of having x over 2 in the middle, we need to have sine x over x in the middle. And then we could use the sandwich theorem, hopefully, because we've got a relationship between 3 different functions. And as x approaches 0, this one is always less than or equal to this one, is always less than or equal to this one. So first off, we could probably clear out all the halves. That might make life a little bit easier. Sine x less than or equal to x less than or equal to, and instead of tangent, just to make life a little easier in the future, I'm going to write that as sine over cosine. Good or no?
Good.
Perfect. Well, I don't need x in the middle. I need sine x over x. Could I introduce a sine x in the middle there by just dividing everything by sine x? Is that okay? Does that mess with my inequalities?
It shouldn't.
No, it shouldn't, because what can you tell me about this angle? This angle is a first quadrant angle, right? And the sign in the first quadrant is always
Positive.
Positive.
positive, right? The sign in the first quadrant is always positive, so I'm dividing by a positive, so that shouldn't affect the inequality signs at all. So we end up with sine over sine, which is 1, is less than or equal to x over sine, is less than or equal to, well, those signs will cancel, 1 over cosine. Good or no? Okay. And how do I turn x over sine x into sine x over x? What do I need to do? I need to take a
Reciprocal.
yeah, just take a reciprocal. I can take the reciprocal of every side. Now that does affect the inequality signs. That actually flips all the inequality signs anytime you take the reciprocal of all the pieces. But we've still got an inequality that has now sine x over x sandwiched between two other functions. Good or no?
Good.
Cool. So using the sandwich theorem, all we need to do is find the limit as x approaches 0 of 1, which was the one that I had on the left-hand side there. What's that limit?
1.
1.
And I also need to find the limit as x approaches 0 of, what was it, just cosine x, right? Yeah, just cosine x, which is the cosine of 0, which is
1.
1, which tells me that the limit as x approaches 0 of sine x over x is also equal to 1. This is a very important limit. We're going to use it multiple times today. You need to have this limit memorized. You do not need to be able to prove it again. You just need to have it memorized. And before we move on to the next problem, I want to go back real quick and take a look at this inequality. If you looked for the limit as x approached 0 of both the outside pieces of this, what would they both be?
Still 1.
They'd both still be 1, right? Which would tell you what about this one that's in the middle?
Also 1.
Also 1. So you're going to want to not only memorize this one that I wrote in blue up there, but also this one. The limit as x approaches 0 of x over sine x is also equal to 1. Both proven using the sandwich theorem. Good or no?
Good.
Perfect. All right. Let's move forward. Let's take a look at the limit as x approaches 0 of sine of 5x over x. So take a second and think about what you might do with that. Any thoughts on what we're going to do with this? Should we draw another unit circle and draw a bunch of triangles and label the angle 5x and blah, 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 and go through that whole process again?
Probably not.
Yeah, that sounds awful. Doesn't that sound like pretty awful? I think that sounds awful. Well, it's still 0 over 0. It's still indeterminate. So we got to do something. What if we made it so that it looked similar to sine x over x, except just that it wasn't x, it was sine 5x over 5x? Could I do that? Can I just do that? Can I just put a 5 down there? You should all be shouting at me, no, you can't do that. You just multiplied it by a 5th and you didn't do anything else, right? I can't do that, can I?
No.
No.
Unless I also multiply the numerator by 5 as well. True?
Yeah.
Then it's okay. Yeah. And let's think for just a second. I was trying to lead you towards having sine 5x over 5x, but now we've got this extra 5. Well, what can I do with that extra 5?
Take it
You
out.
can put it in front of the whole limit.
Exactly. That was one of our properties of limits, right? If you have a constant times a function, which is what I've got, a constant times some function, I can pull that constant out in front. So now I've got 5 times the limit as x approaches 0 of sine 5x over 5x. All right. Well, it's very close to what we had before, except now we have 5x and 5x and x approaches 0. We got to find some way to get around to that still, because I can't just assume that this limit here is equal to 1. So we're going to have to use another technique that we have talked about sometime during this week about limits. Any idea what technique that will be?
Do you use the addition property thing we did earlier and separate it into like the limit of sine of or something? Oh, I've forgotten now. Somehow separate the sine of x on top and on the bottom, so you have 2 limits. So then you have 1 times 5 sort of thing.
No, unfortunately, that doesn't end up working out because we don't really have like an addition going on in here. You could do the division one. You could try the division one, but the division one only works if the denominator limit is not just 0 and it is just 0. So that wouldn't work. It's one of the techniques that we dealt with indeterminate limits previously. So what were some of the things we did to deal with indeterminate limits?
Factor.
Factor, right? That was one of the things. Anything to factor there? Nothing to factor, right? Okay, what was another method we used?
U-Substitution.
U-Substitution, okay. Anybody see a U-Substitution they'd like to try?
5x.
Sounds good. Let's let U equal 5x. If U is 5x, then this is going to become 5 times the limit, which I'll worry about the x approaches 0 in a second, of sine of U over U, right? Sine of U over U is the same as sine of x over x, as long as I have U approaching 0. Well, if U equals 5x and x approaches 0, what does U approach? Also
0.
0. So this could be rewritten as 5 times the limit as U approaches 0 of sine U over U. And this piece right here ought to just equal 1. So we have 5 times 1 or 5. Good or no?
Good.
Cool. So I will tell you that anytime you have something like the limit as x approaches 0 of sine 5x over 5x, that just equals 1. You don't need to write out the U-Substitution anymore. We've shown it works once. It's going to work. If I had the limit as x approaches 0 of sine of x to the 1,000 over x to the 1,000, that's just 1. Right? As long as the argument of the sine and thing in the denominator are exactly the same, you can just make it 1. Sound good?
Yep.
Cool. All right, let's move forward again then to one that's a little bit more difficult. And I keep forgetting, keep meaning every class period to change this. I don't know why I wrote an X there. let's call that the limit as y approaches 0, sine cubed of 4y over y cubed. Thoughts? What should we do?
Can we take the exponent out?
We can. So first off, the sine 4y is being cubed and the y is being cubed, right? So I can't just get rid of it, but for now, I'm going to write it like this. Sine of 4y over y cubed. Would you both agree that if both the numerator and the denominator are being cubed, I could make the whole fraction cubed instead? Hopefully?
Yeah.
Cool. All right. Well, what would I like to have in the denominator down there?
Multiply everything by 4.
Yeah, I'd like to have a 4 down there, so I'll put a 4 down there. And if I put the 4 down there, I got to put a 4 up here. And now what can I do with this 4? I can pull it straight out of all of this nonsense and put it in front of the limit, right?
Yes.
Don't you have
Now, yeah, when I do that, we have something important, though, that we have to make sure we're careful of. That 4 is not just a 4. It's a 4 to the third power. Sorry if I cut you off there. I think somebody was going to ask about that. But yeah, that's 4 to the third power. And now, one of our rules said, if you have an exponent around everything inside the limit, you can take that exponent and put it outside of the limit itself. And 4 cubed is 64. The limit is y approaches 0. Sine 4y over 4y is just 1. So 64 times 1 cubed is 64. Good or no? Any questions, any issues with that? Any problems, concerns, complaints? No? All are good? Okay, let's do another one. You guys want to see if you can try to work through this one on your own? Give you a couple minutes. Okay, cool. I assume you can hear me even though no one's responding. Why don't you take about 2 minutes and work through this one on your own? Let me give you a hint, which is deal with that 4 in the denominator before you try to do anything else. So pull that 4 in the denominator out first. All right, everybody's going to try and do this one on their own, yeah? Then we'll go through it in a minute. All right.
Yeah.
You got like 2 minutes. Ready, go. All right, so the first thing that we should have done was pulled the 1/4 out. So we'll have 1/4 the limit as z approaches 0. And then we would note that the numerator is being raised to the 4th power and the denominator is raised to the 12th. But I could make the 12th as a 4th power if I just made it z cubed to the 4th, which would match up nicely with that z cubed. So we'll have sine 3z cubed over z cubed to the 4th. Good or no?
Good.
Perfect. All right. So then all we need to do is throw in a 3 down here and a 3 up here. And the 3 to the 4th in the numerator gets pulled out as an 81. So we've got 81/4 the limit as z approaches 0 of sine of 3z cubed over 3z cubed, all raised to the 4th. Giving us 81/4 times 1 to the 4th, or 81/4. Do you guys get 81/4? Feel okay about that?
Yeah.
All right, cool. Anybody have any issues there? All right. And what about this one? This one's a little bit different. What makes this one different?
There's addition.
There's addition in the numerator, right? We got 2y plus sine 3y over 4y. So what do you think we want to do with this one? Any thoughts?
We can separate it into two different limits.
All right. So what do you want the first limit to be?
2y over 4y.
All right. So took the first part of the addition and divided it by the denominator. And then the other limit should be sine of 3y over 4y. Everybody good with that? Hopefully. And the 2y over 4y, we can cancel the y. So that just becomes the limit as y approaches 0 of a half. And then this one, we'll pull the 1/4 out. And we've got sine of 3y over y. And what do we need to throw in there?
Multiply by 3.
3 over 3 gives us this first limit is just the limit of a constant, which is a half. And then we've got plus now 3/4 when I pull that 3 in the numerator out. 3/4 the limit as y approaches 0 of sine 3y over 3y, which equals 1/2 plus 3/4 times 1. And what is that? Out of 80? Of course. Everybody good or no?
Could you leave it up for a minute, please?
Sure. Good now?
Oh, yeah.
All right. Here is a completely different one. Any thoughts on how we'll deal with that?
Can you also use like the subtraction rule?
All right, so yeah, first off, what should we have done before we try to do anything is just plug into 0 and we get 0 over 0. So we could try and do the subtraction thing, right? We could do the limit as x approaches 0 of 1 over x minus the limit as x approaches 0 of cosine x over x. Well, if I plug in 0 to this first one, what do I get?
Undefined.
Get undefined. And what if I plug in 0 to this one? I get something else that's undefined,
Yeah.
right? Which is a problem. So that's not going to work out real well here, unfortunately. It's a good idea. Made sense since that's how we kind of did that last one, right? But unfortunately, that will not work here. We've got to go back to some of our tricks for when limits are
Identities?
indeterminate. Say it again.
Identity,
What identity are you thinking?
Pythagorean.
Okay, what Pythagorean identity?
1 minus cosine squared equals sine squared, so we square it first.
Okay, so we can't just square the numerator, right? And besides, if we squared the numerator, that wouldn't give us 1 minus cosine squared, would it? Because 1 minus cosine times 1 minus cosine is actually 1 minus 2 cosine x plus cosine squared x. What would we have to multiply it by to turn it into 1 minus cosine squared?
You'd have to multiply it by 1 plus cosine x.
Right, that's the difference of squares, right? 1 minus cosine x and 1 plus cosine x. And that's like, we did the multiplying by the conjugate, right, for the radicals. And I think at that time I said something like, yeah, it works real nice for radicals, but not cube roots. And we might do this with some trig functions at some point. Well, here's a trig function we're going to do it with. So this ought to give us the limit as x approaches 0 of 1 minus cosine squared x over x times 1 plus cosine x. And conveniently, 1 minus cosine squared from our Pythagorean trig identities should become sine squared x. And now what? What has that done for us? How has that helped us? Any thoughts on what to do now? What's a limit that sort of appears within here that we know?
Sine of x over x.
Sine of x over x, right? I should be able to rewrite this as two different limits. I could make part of it just sine x over x. And if I combine them using multiplication, that multiplication rule, what's still left in the numerator? A sine x, right? And the denominator of 1 plus cosine x. And let's see what that does. What's the limit as x approaches 0 of sine x over x? Should be 1, right? And what about this one? Plug in 0, you get 0 over 1 plus 1. Oh, actually, that's okay, right? That's just 1 times 0, which is 0. So we've got the limit as x approaches 0 of 1 minus cosine x over x is equal to 0. That's another one that you're going to want to memorize. So I'm going to write this here. The limit as x approaches 0 of 1 minus cosine x over x equals 0. Memorize that. And we could have proven this one in almost the exact same way. But if you flip the cosine x minus 1, or flip it into cosine x minus 1 over x, it still equals 0. So you want to have those memorized as well. Everybody good there or no?
Could you go back to the previous slide for just a little bit?
Sure.
Okay, got it. Thank you.
Perfect. Any other issues? Everybody good? So we now have 4 different trig limits that we want to have memorized. The sine x over x, the x over sine x, and then the 1 minus cosine x and the cosine x minus 1 over x.
Will these show up on the quiz tomorrow?
No, nothing we're doing today will be on the quiz tomorrow. It'll only be the first 3 limits assignments. So.
Okay, thank you.
Yep. All right, let's take a look at this one. Do you think we could do something similar with what we did with that sine 5x over x one? with this one? It'd be nice if that denominator was not just an x, but a
10x.
yeah, 10x. So we'll put a 10x down there. I put a 10 in the denominator, I got to put a 10 in the numerator. And what can I do with the 10 that's in the numerator now? Take it and throw it out in front. Everybody good with that so far?
Yep.
All right. So we could do the U-substitution, and we'll write it out here. Let's let U equal 10x. And as x approaches 0, what does U approach?
0.
0.
Should also be 0. So this can become 10 times the limit as U approaches 0 of 1 minus cosine U over U. And we could see that just like with the sine x over x ones, we can always turn these into the U subbed limit. So you don't need to write them out anymore. That one just becomes 0. Good or no? Any
So-
issues?
Basically, this is relying on the limit that we proved in the last problem.
That is correct.
Okay.
All right. Let's look at another one. This one looks a little more complicated, doesn't it? Maybe just a bit.
Yeah.
But with a careful eye and a mathematical mind, you should recognize this. No? Bummer. All right. Let's put a new page in here then. All right, we're going to start off easy. What is this?
1.
That's right. That's a 1. All right, good. What about this?
1.
That's good. What about this?
1.
What about this?
1.
1.
What about this? What goes here?
2.
2.
Why?
1 plus 1 equals 2.
That's right. And a 1 here, and then a 1 here, and then what goes here?
3.
3,
3, and a 2 and a 1 gives us another 3, and then a 1, and then a 1, and then a
4.
and then a 6, and then a 4, and then a 1, and so on, just by adding the two numbers above. This should be something that you have seen before in the past. This is Pascal's triangle. Yes, you've all heard of, seen before, are familiar with Pascal's triangle?
Yeah.
Yeah, you probably had a math teacher that was like, look, it's a cool triangle, and look, you can get these numbers, and then, I don't know, they might have told you something else about it, maybe. There are lots of good uses for Pascal's triangle. It's like super useful in like probability theory, and you know, how you, if you're trying to choose a certain number of, you know, marbles out of a bag, that's just a basic thing, right? But like choosing a certain number of colored marbles out of a bag, how many of each color you have in there, and blah, blah, blah. You can use numbers from Pascal's triangle to help you figure out the probability of picking a certain colored marble, let's say. But it's also really, really useful in algebra. Why? Well, here is a plus b to the 0 power. What does it equal?
1.
It should just be 1, right? And here's a plus b to the first power. What does that equal? It's a plus b. And what's a plus b to the second power? a squared plus 2ab plus b squared. And what's a plus b to the third power? A cubed plus 3a squared b plus 3ab squared plus b cubed. Right. These numbers in Pascal's triangle give you the coefficients of the expansion of a binomial to any power, right? Coefficient on 1 is 1. Coefficient on the a and the b are both 1s, right? 1, 2, 1, 1, 2, 1, 1, 3, 3, 1, 1, 3, 3, 1. So the next one, a plus b to the fourth, ought to be a to the fourth plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the fourth. Good or no? Okay. What if this was a minus? Then they just alternate. Positive, negative, positive, negative, positive, negative if I had another one, right? You go down as far as we wanted on this triangle and get out the expansions of a binomial to a power. These numbers are used in what we call the Binomial Theorem. You've all heard of that before, maybe? Maybe, maybe not. Whether you have or not, you should at least know these coefficients for the expansion. Everybody good with that?
Yeah.
Cool. So if we look up here, oh my gosh, what do we have? We have a 1, a 4, a 6, a 4, and a 1 as my coefficients, which tells us that this should be an expansion of a minus b to the fourth power, right? Because we've alternated positive, negative, positive, negative, positive. So this ought to be a minus b to the fourth, with a equal to what and b equal to what?
A is 1 and B is cosine of x.
Perfect. So this limit now becomes exceptionally easy. Just factor that numerator out. Take the power. Around everything. And it's just 0 to the fourth, or 0. Good or no? Any questions, issues, problems, complaints, concerns? No?
Nope.
All right. Let's do this one. This will be a fun one. Any thoughts? Nobody has a thought on this one?
Can you separate the numerator and denominator?
All right, what do you mean by making it two separate limits, the limit of the numerator divided by the limit of the denominator?
I was thinking, like, if you multiplied limit of the 1 over sine 10y and then multiplied that by limit of sine 4y over 1.
Sine 4y over 1 and times 1 over sine 10y, right? Now, I know you said separate limits, right?
Yeah.
All right. I'm going to hold off on the separate limits just for a second, but we are going to put them into separate limits in just a second. So with any luck, looking at this, we would note that the first piece of it is very close to being a nice easy limit, as is the second piece of it, right? They both just need some stuff added in. What needs to be added into the first one? What do I need to multiply this denominator by?
4.
Not just 4, but for
Y.
y, right? And what about the numerator up here?
10y.
Y.
Needs a 10y, right? Yeah. Cool. So I multiplied the top by 10y and I multiplied the bottom by 4y. Well, those don't quite cancel out, right? The y's are good, but the 10 and the 4 are not. So I also need a 10 down here and a 4 up here. Everybody agree with that?
Yep.
And then we'll just take those extra 4/10 out, which we'll reduce in a second. And now we will turn it into the two different limits that you wanted it to be, now that we've built in easy limits to solve. And 4/10 becomes 2/5, right? And 1 and 1. Good or no?
Good.
Hopefully good. All right. We are going to throw in an extra page here, and I want you guys to help me out with finding this limit. Any ideas with that one? How about we rewrite the tangent? Wouldn't that be the same thing?
Yeah.
Yeah, should be the same thing. And we could rewrite this as two different limits. And evaluate both of those. What's the limit as x approaches 0 sine x over x? It's just 1. And what about the limit as x approaches 0 of 1 over cosine of x? Well, that's just also 1. So we should now also memorize this limit. And I will tell you that the inverse of that is also true. Two more limits that we should memorize. So we now have 6, right? Sine x over x, x over sine x, tangent x over x, and x over tangent x. Those limits, as you approach 0, all equal 1. And then the limits as x approaches 0 of 1 minus cosine x over x and cosine x minus 1 over x both equal 0. Everybody good with that?
Yep.
All right. I think then last problem for the day, I will give you guys 1 or 2 minutes to work on it, then we'll go through it, and then we will call it good. So you have 2 minutes to do this problem. Ready, go. So we will take this one and separate it out like we did with the sine one. Tangent 3x over 1 times 1 over tangent 4x. And in order to make these nice and simple limits, we'll put in a 3x and a 4x. The x's cancel each other out, which is good. The 4 and the 3 do not, so we'll add the 4 in the denominator and the 3 in the numerator. And we'll pull out that 3/4. 3/4, the limit as x approaches 0 of tangent 3x over 3x times the limit as x approaches 0 of 4x over tangent 4x. And what should both of those be?
1.
Yep, we could do that same U sub that we've done in the past, but we also don't have to do that. And we'll get 3/4 as our answer. And that will be it for today. Any questions?
No.